Hello, my name is John Huntley. Over the next few minutes I'd like to give you an idea of some of the projects we've been running in this research lab over the last few years for the undergraduate Part C projects. So every student in their third year will take a project and it takes between a third and almost a half of their time, depending on if they're in the BEng or the MEng programs. And this particular lab we're in now it's a research lab. It's been associated with a program a project that's been funded by the UK government, over £10 million. So we have really nice equipment here. Here we have a standard industrial robot. This is a scanner, call it a scanner, 3D scanner, which we've been developing in the group here over quite a few years now. It basically projects patterns onto the object, and then there's a camera built in this. What you're seeing here is the end of that tube. Inside the tube there's a camera and a projector. The camera is recording images all the time, and by using various algorithms it can actually work out the three-dimensional shape of an object without making contact. So it's quite a powerful technique. You basically end up with a 4 megapixel image with not just grayscale or colour information, but also XYZ coordinate information. And so what we were doing so I'll show you first of all the project involving the robot and the scanner. So the task we set the student, it's a third year student as I say, in this particular project was to basically to integrate these two systems, to use the scanner here as the essentially the eyes, the three-dimensional eyes for the robot. So when robots are used in industry at the moment, they're very good at moving from sort of A to B, thousands and thousands of times a day. What they're less good at is being able to adapt to changes in the surroundings. So, for example, if you have a part that arrives, if you have a bin with lots of parts in it, and they can be arranged at random, or you may have things which have sort of variations in size and in geometry and so on. How do you get the robot to be able to cope with those sort of how does it adapt to the change in surroundings? So that's really what this project was all about. And so sort of the task we set the student was, we've got these wooden balls here. So can you get these just arranged at random, can these be placed, can you get the robot to pick them up and place them on these cups just here? Okay, so sounds like a trivial task, but it's not that trivial. And so the student has several tasks, several stages. So one of the things was to sort of mechanical design. How do you get the robot to actually pick up these wooden balls and then release them just above the cups that I've just shown you? So this is part of the solution. So it's basically like a glorified drinking straw. There's a vacuum generator that was installed on the robot, which can be turned on and off under computer control. And there's this, so it's like a drinking straw. They say this is placed over the wooden ball. You turn the vacuum on, it grabs the ball, then it moves around. Turn off the vacuum, and the ball drops down into onto the cup. So that's the theory. Now there's several other challenges to get that to go. So the other challenges were, well, these two systems have completely different coordinate systems. How do you align them? So we had to come up with a procedure for aligning those two coordinate systems, the scanner coordinate system and the robot coordinate system. Some software development required as well. So the 3D images, these 3D images coming from the scanner, these have to be then segmented, and there has to be some sort of recognition going on to detect, well, these are this part of the 3D image corresponds to the sphere and this part to the table and so on, so that it can recognise and then can work out, by a process that we know called least squares analysis, we can work out and estimate the centre location of each of these spheres. So having done all that, he was then able to integrate this, or bring it all together, so that by the end, just before Easter of this final year, he was able to get the whole thing working. And I'm going to show you a video clip of that of the robot in action. Another project that we ran here, another bachelor's project, was to design and build and then use this device here. So you might be wondering what this is here. This is actually a calibration device. So when you make a scan with one of these scanners that we've just seen here, you will typically position something on a rotary table just in front of the scanner, because the scanner can only see one side. It's a camera and projector after all. And then you'd rotate the part a little bit, and then you'd do another scan, rotate a bit, do another scan, and so on. And you end up sort of getting this maybe a dozen or so scans going all the way around. Now the drawback with that is that the errors sort of accumulate, so that when you get to the 12th scan, all the way around, you find it doesn't quite match up when you try to register them. It doesn't quite match up with the first scan, and so measurement error with these sorts of systems is something that we've been trying to work on to improve the accuracy and get it close to the mechanical coordinate measuring machines, which are sort of the workhorses of the traditional metrology lab. Typically a few micrometers is the accuracy, whereas with the scanner here you can get maybe 100 micrometers. So we're trying to improve the accuracy. So to do this, one of the things we wanted to do was to see if we could have, instead of just simply linking all the scans together one after the other, we could have some sort of global optimization to sort of to link all these into some, so that we basically distribute the errors over the whole pod. And as part of that process, the student here designed this calibration device. And so the idea is that the scan, when you do the scan, each of these little circles here, we can work out from the scanner the 3D shape of this part. We can work out what the scanner believes the center points of the XYZ coordinates of those points is, and then we can compare that with a mechanical CMM or coordinate measuring machine that can go and actually touch all the way around these cylinders and work out what it believes the center coordinates to be. And so the project here involved doing some quite detailed design work to make up all these plates. They're all made up on the CNC machine, beautifully made, sort of chamfered, they all fit together very nicely. And then the student did quite a few scans with the scanner, this scanner just here, and he wrote some code, some MATLAB code. That's the programming language that we teach to all our second years, to improve the registration and reduce the errors that accumulate as you work around all the way around a scan in the traditional way. Here's an example of one of those 3D images I've been talking about earlier on. It's color-coded, so this is the view from the scanner. You can see in front you have the tray with the wooden balls in. Those are colour-coded blue because blue indicates that those points are closer to the scanner. Going all the way through to the red screen at the back, that's colour-coded red because it's further away from the scanner. Another project that we ran a couple of years ago is to do what we call finite element analysis as part of the design work for a calibration panel. So the particular device we're trying to design was one of these panels here. So this is basically think of it as like a two-dimensional ruler, because when you first set up the scanner, it doesn't have any information at all about the dimensions of the part it's making. So this is the way that we can tell it that the answers that come out are in units of millimeters or whatever. And so we have this array of holes which are positioned, this array of circles, white circles, sorry, on a regular grid on the plate, and those are measured independently by another device technique called photogrammetry. And so this device can then be positioned in front of the scanner. We can do a scan, we move it around, up and down, tilt it around. Each position you have a scan, and then you go through a process of combining all that information to calibrate the scanner. Now the problem is that as you move the part around, if this is in this orientation or in this orientation, you get a difference in the position that actually moves a little bit due to the gravitational loading. So if you imagine it in this position, it's the extreme case. It's a bit like with a tablecloth drapes over a table. The corners sort of droop down a little bit. Not very much, because this is made of it's a honeycomb structure, but nevertheless we had to design it so that the gravitational deflections were small compared to the measurement accuracy. And what you see on the left-hand side here is the output of an FEA, or finite element analysis model developed by the students for this particular honeycomb structure. And so by varying the thickness, by varying the mechanical properties, we're able to come up with a design which fulfilled the the deformation requirements, the maximum deformation criteria. And on the right-hand side here, you see this is actually a master's student project. That was designing the carbon fibre tube. Carbon fibre has great mechanical properties in terms of weight to stiffness ratio, but it's also can have very good thermal properties as well. And that's one of the issues with this setup. You've got quite a hot projector inside the tube. Think about all the hot air that's flowing around inside the tube, and what effect will that have on the relative position of the camera and projector. That ultimately will affect the accuracy of the system. And then this final example, this was a project run with the Sports Technology Institute. So, of course, Loughborough is well known for its sports research. They have all sorts of equipment over there, including on the left-hand side here. This is a device for kicking a football many times. And so for this particular project, we're interested in looking at the difference between some traditional stitched leather balls and thermally bonded balls, so a newer manufacturing process. So this involved using the scanner to measure the shape of the football at various stages after the football had been kicked a few hundred times. And what you see on the right-hand side is the deviations from the best spherical shape that you would ideally have, colour-coded to show deviations in millimetres away from the best fit, best spherical form.